Hello, I'm Neal Skipper from University College London, and I'm a member of the Clay Minerals Group, which is a special interest group of the Mineralogical Society of the United Kingdom and Ireland. The Clay Minerals Group was founded in 1947, and so 2022 marks its 25th Jubilee year. As part of the celebrations for this landmark, we are conducting 12 interviews to highlight the diversity of minds and hearts behind the wonderful world of clay mineral research and its applications. Today, it is my great pleasure to introduce Professor Lynda Williams from Arizona State University in the USA. Lynda was awarded her bachelor's in geology from Smith College in Massachusetts and her master's in geology from Dartmouth College in New Hampshire. Lynda completed a PhD in geochemistry at the University of Calgary under the supervision of Professor Ian Hutchin. Lynda held research positions at Argonne National Laboratory and Louisiana State University before moving to Arizona State University, where she is currently a research professor in the School of Earth and Space Exploration. Among her many awards, honors, and accolades, Lynda was president of the Clay Minerals Society in 2018 and is their current Bailey Distinguished Lecturer. Lynda, welcome and thank you so much again for agreeing to this interview.
Thank you very much for inviting me.
It's a pleasure, so thanks again. So to start, I'd be very interested to learn a little bit more about your route to becoming a clay scientist. So perhaps if you could just explain a little bit about what inspired you to enter clay research and how you were introduced to the wonderful world of clays and clay minerals.
I never intended to be a clay scientist, actually. I was in mineral exploration, working in the state of Maine, and I worked with a professor from Dartmouth College named Half Zantop, and we were looking for base metal sulfide deposits. He invited me to apply to Dartmouth for a master's degree. And when I went there, everyone was forced to take a class in clay mineralogy with Bob Reynolds, who I consider the grandfather or pioneer of clay science in the US. And it was I remember saying, why would I take an entire class studying just clay? And I learned a lot in his class that just clay is not just clay. It opens a whole world of geochemistry, mineral water interactions. There's so much that we can learn from clays that I got fascinated with using that. And my master's was on looking at ammonium in the interlayers of illite smectite, which is increased around massive sulfide deposits that are in black shales. And so that began my interest in organic, inorganic interactions in clay minerals.
Great, thanks very much. Yeah, there's an infinite variety in clay minerals, and you've researched very many aspects of these materials. I wonder if you could just outline what your current main research topics are and what your interests are in the field.
Sure. Stemming from the study of nitrogen, ammonium in clays, I worked in the Basin Research Institute in Louisiana. And of course, the only thing you can study in Louisiana is oil, right? And there's plenty of ammonium associated with oil. So I got interested in using ammonium and nitrogen isotopes in the clays as a way of tracing hydrocarbon migration paths through the sandstone reservoirs. Then when I came to Arizona State University in 1991, I worked with someone here, Richard Hervig, who is the master of the secondary ion mass spectrometry. And he develops techniques of looking at in situ isotopes in solids. But he had never worked with clays. And he happened to be working on boron. So I started reading more about boron in the clay minerals. And it turned out Bob Reynolds, my advisor, had done his dissertation on boron in clays in a different way, just looking at boron content, not isotopes. And then I said, we began studying lithium as well. And the importance is that Ammonium goes in the interlayer of illite smectite. It goes in, boron goes into the tetrahedral positions, substituting for silicon or aluminum, and lithium goes in the octahedral site. So my thought was, if I could look at the isotopes as crystals grow, then I can answer the question, is there wholesale dissolution reprecipitation during illitization of smectite, for example? If so, then you would see a change in all three of those isotopic systems versus a solid state transformation where you might see a change in one but not the others. So that was the first, I don't know, 20 years. I was funded by Department of Energy to study boron and lithium isotopes in clays, and then also by National Science Foundation. So a lot of my background is looking at clay minerals in different size fractions, less than 20 nanometers, 20 to 50, 50 to 100 nanometers. That's where you get rid of the detrital materials and you can assess the crystal growth. And working with people in Europe who do dating of clay minerals using potassium argon, we have shown that the isotopic changes in those size fractions can be as much as 80 million years, just going from the finest to the more the largest size fraction, which is most recent. And so you can determine the paleofluid compositional changes over that time. And there's a distinct isotopically light signature when hydrocarbons enter a system, for example. And so if you see changes in the different size fractions, and one is incredibly more light than the others, then you can suggest that that's when the hydrocarbons came in and you can date it. So it's really remarkable that you can get an entire geologic history from one hand sample, one core sample.
Yeah.
That's part of what I do now. I have a student finishing up his dissertation on lithium in Kerogen. But also in 2002, I became interested through the Clay Mineral Society in antibacterial clays. And that happened because a woman in France was curing people with a terrible flesh-eating disease, and she was in Ivory Coast. Her husband was a diplomat there. And she wrote the Clay Mineral Society and asked if anybody knew why clays kill this bacteria. And nobody answered. And so 6 months later, her son, who spoke English, she didn't speak English, wrote and said, I guess no American clay scientists are interested in poor people in Africa. And that got my attention. So I said, well, I don't know anything about medical applications of clays, but I have a microscope and I can look at at least what kinds of clay minerals are in this clay that's healing. Because he thought that they were fibrous and that they were just stabbing the cells of bacteria and killing them, as he called them, nanoscalpels. And I found they were not. They're nice hexagonal plates of illite, small, 200 nanometers across. And I think that that's important to the whole process, is that the small crystals are interacting with the fluids and dissolving and providing the reactants that are killing the bacteria. So I've been studying that for 20 years now.
Yeah, it's incredible, isn't it, that they work in that way, and that
Yeah. Yes, and then determining, is it just this one French green clay she was using? No, it's all clays that have reduced iron. And, it can be a kaolinite or it could be an illite smectite. The ones I've seen are predominantly illite smectite, and particularly 50-50 ordered illite smectite. And so one question is why? Why is that this rectorite is called more effective at this process? And I think it's because of the 50-50 structure. The mineral structure itself is more prone to dissolve, and when there's 50-50 ordering, and so it's releasing more of its reduced iron, and aluminum is involved as well. And so it's really an interesting progression.
Yeah, fantastic. So, I mean, just looking a little bit more broadly, what other sort of main challenges do you think we still have in clay science? What big questions are still there to be answered?
Yeah, and that's a tough one to answer, but because there are so many things, and it sort of pains me that I see, at least in the US, the number of people studying clays and clay minerals is going down. At least the members of our society is going down, and I think that's, maybe it's not true in Europe, but I think it's because people are not understanding that clay minerals are the nanoparticles, that if we understand their natural processes in all kinds of things, global climate change and CO2 sequestration and all of the organic, inorganic interactions, if we understand the natural processes, then we can apply and design new materials to absorb CO2, for example, another thing, I'm in the School of Earth and Space Exploration, so a lot of my colleagues study other planets and meteorites, and I'm shocked at the level of misinformation out there about clays and clay minerals in meteorites, for example, and basically think that if we study more of the isotopes of these clays that are found in these materials, we can get more information about the formation of those planetary bodies, and even the evolution of them over time, if you're looking at different crystal sizes. So I'm hoping that we can get more young people interested in clay science, and as they, like I thought, why would I study clays? They're just clay. They're just a door opening to all these fascinating physical properties and events that we are concerned about.
Yeah, they're the archetypal nanoparticles, and I think
they are nanoparticles. Yeah. I am a grandmother now, and my name is Nano to my grandchildren because I study nanoparticles.
Well, maybe they'll be recruited.
Yeah.
I mean, I think we sort of, you've addressed this already, but maybe just highlight the grand challenges that you think that clays can help us address, or what we know how it is that they fit in our.
That's all I can say is that as far as grand challenges, I think that we need to understand clay processes more. Well, for example, in my research in how clays are killing bacteria, but furthermore, improving the rate of healing in wounds, at least some wounds. And I think it has to do with electrochemical properties. And I think this is a major area that people have not thought about. People are often talk about pH changes and the changes in clay chemistry, and I know there are plenty of people studying electrochemical properties, but I think that in combination with the human tissues and human illnesses, it has a lot to offer in the future of designs of new medications or new wound healing bandages and things like that. There's our research is sort of at an impasse right now. We had a research showing that the antibacterial clay that kills all the antibiotic resistant bacteria that we had studied doesn't work in the wound. And we did several trials with mice. And so overcoming that, I think that we can make it work in the wound, but we have to understand what are these reactants complexing with in the wound, and how do we get rid of those complexes so that the healing process can proceed. So there's a lot of research out there to be done.
Yeah, I think that's always the case, isn't it? That the deeper you look, the more there is to understand.
Exactly.
Yeah. So looking back a little bit now, so we've sort of taken us through a look forward. If you look at your research career in clays, what's your proudest moment? What gives you the most satisfaction from your research?
I would say that what I'm most proud of always in my research is following my curiosity. And when I started the antibacterial clay research, I'm from a family of medical doctors, and my father's a neurosurgeon. And he said, "You're crazy. People are going to think you're a quack studying how clays can be used in medicine." And I said, "Yeah, but Dad, I'm a scientist." And this is an observation. I have photographic evidence that these wounds are being healed over time when you apply clay. And so I have to formulate a hypothesis and test it. And I don't think I could be criticized for that. And it turned out that there's a lot of new, it's sort of opening a new area of investigation to I call it geomimicry, just to look at the minerals in nature and how are their processes working so that we can copy them and make advances in what's important to society.
Yeah, I think the curiosity driven is always a,
Don't be afraid to follow your curiosity. And sometimes it's hard to get funded. It was very hard in the beginning. I had to go to the National Institutes of Health and talk to a program director, and she gave me 20 minutes. And so I talked to her about clays, and I showed her pictures of crystal and clays. And she said, "Clays are minerals? Clays are crystals?" She had no idea what it was. And that's the director that would decide whether or not I could do the investigation. So, and that's the other thing, you need to go talk to your program directors, because once you get them on board, then it's much easier to get funded.
Yeah, I think getting funded is always going to be a challenge,
yeah.
Isn't it? No.
It's one thing to follow your curiosity, but you have to get the funding.
Yeah, particularly with interdisciplinary research like this was. It's
yes, and that's it. Yeah, that's the other thing. Interdisciplinary research. We don't speak the same language. The microbiologists I work with, talk about OD, and they're talking about optical density, and to me, that's the outer diameter of tubing. Yeah. So we have to get on the same page with our language.
Yeah. So that was a great success, and obviously the flip side, I think, especially when you follow curiosity, you do have avenues of research that don't work out as well as you'd hoped. So can you think of any instances where that happened and what you learned from that?
Well, I do hydrothermal experiments on clays, and so there's failure all the time. In fact, only 25% of experiments actually work. You have all kinds of issues with the experimental apparatus, or for various reasons, you'll do an entire 6-month experiment and get no useful data out of it. And that's always disappointing. It's especially hard when it's students who are doing it and they're in a limited time to get their degree done. And but that's part of the whole thing. I try to teach them that not everything goes as planned. And if it did, then it's too easy. Everyone's done all the easy stuff, only the hard stuff is left. So yeah, we have failures. Also, I was very disappointed that the antibacterial clay that I've been working with, that's killed everything in vitro, is not working in vivo. But I don't think that is necessarily a failure. I think that is a roadblock that we have to overcome. And so I see it more as a challenge to continue this work and figure out how to get around that problem. To do that, you have to understand really the mechanisms, the antibacterial mechanisms precisely. I mean, I know that iron and aluminum in Fenton reactions are destroying the bacterial membrane and interior cellular proteins in DNA. But I don't know why the bacteria are not defending themselves when they have all kinds of mechanisms to defend themselves. And from that side, I don't know enough about the microbiology to answer those questions. So my solution is we have to do interdisciplinary research. We have to be able to work as a team with microbiologists and medical scientists and apparently wound healing specialists who don't consider themselves medical. They're more pharmaceutical, and I didn't even know that. So we have to be able to work together to overcome these challenges.
Yeah, I think it's an excellent point that we shouldn't regard them as failures. They'll often, a negative result can often be more interesting than maybe a positive. Yeah. So changing tack a little bit, we've all got our favourites, and I wondered if you could just explain which your favourite clay is and why.
Well, I'd have to say smectite, because smectite is. I once wrote a paper. What was the title of it? It was called calling smectite the primordial womb. I was interested in origins of life because ammonium goes into the interlayer, and ammonium can be involved in reactions that form biomolecules that we need for the origins of life. And so I think smectite would be my favorite. If you look at clay, Bob Reynolds and Dewey Moore's book on clays, X-ray diffraction of clays, they call it the princess of clays. And I agree with that. Just because smectite is the beginnings and it evolves into illite, and all kinds of interesting reactions go on in that interlayer, what I call womb, organic reactions, organic synthesis. We once put ammonium and methanol into a reactor and made methyl stearate after, at 300 degrees and a kilobar pressure in a month's time, you come out with methyl stearate. So that's important in cell wall building. So I think there's a lot more research to be done along those lines as well.
Yeah, same here. I think smectite is just a wonderful material, isn't it? So flexible.
It is, and so many different ways to be used, and for human societal benefits, to put microbes in there and get the smectite to become illite and stabilize the soil, I think is fascinating. Yeah. There's all kinds of research that smectite is important.
Yeah. So now looking, I guess, sort of reviewing and looking back a little further, from what you've learned in doing clay science, would you have any suggestions or thoughts for someone who is just starting out in this field, or maybe was even thinking about going into the field at an early stage in their research career?
Yeah, and following along the lines of what I just said, I think that people, maybe they're not interested in clay minerals, but they don't understand that clay minerals are all minerals. It's of a particle size, and that, clays are, and that clay minerals are in that fraction, and they're the more reactive of all those minerals. But altogether, it's mineralogy at the nanoscale. And you can't stop with just understanding the mineralogy. You have to understand the physics and the chemistry and the evolution of these materials over time. They need a broad background. I think I'm always pulled between depth of knowledge and breadth of knowledge. And we're going to be pulled both ways, that we have to know our science in depth and be broad enough that we can reach across the interdisciplinary boundaries and speak to the medical researchers or the astronomers or whoever it is that need to understand what we know. We have to learn communication. So I would say, learn all you can and explore what excites you.
Right. Yeah. Yeah, I think that's obviously wonderful. Yeah, that's wonderful advice. I think the breadth versus depth is always challenging, isn't it? So now just sort of looking more generally, we've talked a lot about clay minerals. I wonder if you could just expand a little bit on what you do outside clay minerals. I guess what other research topics or anything that how you spend your time outside clays.
I hated that question, actually, because I'm about to retire at the end of this year. And I thought, well, what am I going to do in retirement? I don't think I can stop this. So retirement is going to be a gradually phased out. I love research. But I used to, I saw one of the interviews that you did earlier, the woman talked about being a ballerina when she was younger. And I'm surprised at all of the geologists I'm finding out that started out in ballet. I did, it was a ballerina for 17 years. Started when I was 3. And so I was physically active in outdoors activities and a swimmer in my early years. And I have to say, I don't do that anymore. I have artificial knee, I can hardly get around. But now I think that when I retire, what I'll focus on is gardening, which I love, and grandchildren. And so that's my job, is to raise some good young scientists, my grandchildren.
Well, good luck. Yeah. And the last question is, obviously, thanks again, for being, willing to be interviewed. If you had, if you were choosing someone you'd like to interview or talk to about clays, who do you think that would be?
I previously said you, but I got to talk to you today, so that's
Yeah.
I always love to talk with Fred Longstaff. He's at Western Ontario, and he was really instrumental in getting me interested in isotopes in clays and clay minerals. He studies mostly oxygen, hydrogen isotopes, and in traditional ways, not solid state mass spectrometry. But he's always fun to talk to, and he's full of stories of interest. So I think he'd be a great person to interview.
Right. So thanks very much again, Lynda. That was a real pleasure for us, and we appreciate very much you taking the time.
And my pleasure, and thank you for doing this, because it's an important contribution to clay science and the community. And I think that it will be worthwhile for many years.
Thank you very much again from everybody in the group.
Okay, thank you.